Good afternoon. I'm making a video because I'm not able to attend. You, like me, as far as I understand, want to make a quantum computer, and you, like me, want to make it in silicon. We want to make use of superposition and entanglement, and make an entangling gate. So we want to act on the qubits, such that the final state of one depends on the initial state of the other. And one of the simplest ways of implementing the controlled Z gate is to only induce an interaction if both the qubits are in spin down or spin up. The qubits might be the donor electron spins or the donor hyperfine states. If we know the exact value of the interaction, then we can induce the interaction for a duration proportional to it. So the value of the interaction, E times T equals pi. So e to the minus I e t equals minus 1. And not induce an interaction if the donors are in any other initial state. But the exchange oscillation, the exchange interaction, oscillates wildly in silicon. And this is limiting because, as we said, we need to know the exact value of the interaction. So even with the most precise donor fabrication techniques, hydrogen lithography, we can't position the donors more precisely than to within 6 lattice sites for phosphorus or 2 lattice sites to arsenic. And if you want to look at a fabricated 2-donor device or multi-qubit device, this is a problem. With Alex and Nguyen, under the supervision of Andrew Fisher, we borrowed some ideas from cold atom implementations. The Rydberg blockade entangling gate doesn't depend on the exact value of the interaction. It only depends on the interaction being larger than a certain value. You can imagine the pulse sequence which is proposed in the Yapsh paper of 2000, where they proposed the entangling gate. It applies a pi pulse to the first atom, a 2 pi pulse to the second atom, and a pi pulse to the first atom to bring it down from the excited state again. If both atoms are on resonance with the laser, the first atom gets excited, the second atom tries to get excited, but maybe they're very close together, and their interactions are so large that it's off resonance. Actually, this interaction would induce a small phase, but the larger the value of the interaction, the smaller the phase, the more negligible it gets. And so you're in a state where you can excite the first atom, but not excite the second. So you can see now, if both the atoms are off resonance with the laser, none of them get excited through this pulse sequence. So the final state is the same as the initial state. If one atom is on resonance with the laser and the other is not, so we have the excited state on resonance, so we have the spin-up state on resonance and the spin-down state not on resonance. If one atom is on resonance with the laser, then the pulse sequence will give the final state a minus sign compared to the initial state. And same thing the other way around. And if both atoms are on resonance with a laser, only one can get excited. So we also acquire a minus sign. The condition for this blockade gate to work is that the value of the interaction, the theoretical interaction, which the donors would have if they were both excited to the Rydberg state at the same time, is larger than their Rabi frequency, and that their Rabi frequency is larger than their decoherence time. So what is the value of the interaction required to get high-fidelity Rydberg entangling gate? We simulated it using the Lindblad equation and using experimentally determined decoherence time for excited states of donors in silicon, of phosphorus and arsenic in silicon, which is about 200 picoseconds. This is phonon limited. And you can see from the fidelity of obtaining or of being able to prepare this Bell state, you actually need very large interactions between the 2 donors. And for phosphorus donors, these are very, very large interactions. So we simulated the electron wave functions using a finite element method. We got the different wave functions of different donors, different donor types in silicon. And so we chose a very high principal quantum number because we wanted large values of the interaction. And in the 10SA state, it looks like the values of the interaction would be large enough. But perturbation theory is not strictly valid here because the binding energies of the donor of phosphorus are in the tens of MeV. So more rigorous electronic structure calculations would be necessary here to really confirm that this gate is possible with phosphorus or arsenic. Spin selective excitation is also required for the gate, and this is tricky in phosphorus because it doesn't have any spin orbit coupling, and so a magnetic field would split the ground state and the excited states equally. But you could imagine schemes going via the D0 X state with 2-photon excitation, and these have been proposed. So, selenium plus, however, is a double donor, which is 2 protons and 2 extra electrons than the silicon lattice, of which 1 electron has been ionized. So there's 1 remaining electron feeling the potential of 2 protons, pulling it right in towards the core. So it has large binding energies. And on top of this, the binding energies are around hundreds of MeV. So we're going to be able to use perturbation theory, hopefully. On top of this, it's been experimentally demonstrated that we can go from the 1SA state, which has large hyperfine splitting, giving rise to a natural qubit basis, to the 1st2 gamma 7 state, which is forbidden in effective mass theory. And here it's been experimentally demonstrated, and on top of this, we would use the 1st2 gamma 7 state as the rydberg state. It's got a relatively long lifetime of like 7.7 nanoseconds. So it looks like the ideal platform. So what are the values of the interaction required for implementing a high fidelity Bell state? We need to be above 1 MeV, or preferably above 10 or 100 of MeV. This is possible to simulate using perturbation theory, or to calculate using perturbation theory because of the very large binding energies. But the exchange interaction is not large enough, also because of this very, very small Bohr radius. So we'd like to borrow something else from cold atom implementations, or the rydberg community. Dipole interactions. Dipole interactions decay as a power law and not as an exponential or wildly oscillating exponential, which is really nice because they'll still be large at values of interdonor distances where the exchange interaction is already small. Direct dipole-dipole interactions decay as 1 over r to the cube, and second order dipole interactions such as van der Waals decay as 1 over r to the 6th. If we induce an electric field, the dipole moments become even larger. And so applying an external electric field really creates much larger interactions. So we simulated the van der Waals interaction between 2 donors of selenium plus in the 1st2 gamma 7 state, and it looks like their interactions at relatively small distances are large enough to create a gate. And what's more, it's quite exciting that the selenium plus, of course, has this extra proton, and that will create an intrinsic electric field for the other selenium donor. So actually, we don't even need to apply an external electric field. We can just, it has an intrinsic electric field which induces large dipole moments, which gives rise to large dipole-dipole interactions, which are large enough for implementing a high-fidelity rydberg blockade entangling gate in selenium plus. And if we wanted the interactions to still be large at even larger distances, so on the map, donor 1 is positioned at 0, 0, and all of the other locations are the other possible locations of the second donor. So you can see we get above 10 or even 100 MeV. And if we wanted those interactions to remain large at even larger distances, we could apply an external electric field. That's quite promising. Thanks for listening, and I would be happy to answer any questions via Skype or via email. Bye. Have a nice evening.